Okay, good afternoon. Let us start our lecture. Just to remind you, we have our midterm test tomorrow evening. Start at 8 o'clock. MPSH 2, right? So it's a multipurpose sports hall 2. Yeah, we have uploaded the sitting plan, so please refer to the sitting plan before you go for the midterm test. Okay, so last week we start talking about special distribution, special or common distributions. These distributions are very commonly encountered and are used to model practical problems. So we briefly talk about discrete uniform distribution. Uniform means that every outcome has equal probability or probability measure. So for discrete case, each possible values for the random variable takes same probability, equal probability of taking that value. So it's uniform. So another type is very important, is binomial distribution. And binomial distribution is based on something called bilinear distribution. Bilinear distribution, all right, is the simplest distribution that we can think of, because the bilinear distribution takes on only two values. All right. So because in a lot of situations we have the outcome either considered as a success or failure. So two possible outcomes. In fact, if you want to be different from a constant, at least you must have two values for that variable. So a random variable is a variable which has at least more than one value. So the smallest number of possible values is 2. So we take it as success or failure. Or if you want to use numbers, then we use 1 to denote success and 0 denote failure. All right? And then for each value, 1 or 0, you attach a probability. So we convenience code the outcome as 1 and 0. So which one is 1, which one is 0, it doesn't matter. It's just like when you define what is a success, it's up to you to define what is considered as a success. All right. So random variable x, all right, to have a bilinear distribution if the probability functions is given by p raised to power x times 1 minus p raised to power 1 minus x for x equals 0 or 1, and f of x equal to 0 for other x values. And this p is called parameters. Okay, a parameter basically is a constant. It's a constant, remember, it's a constant. Different values of these parameters will indicate different distribution. All right, so there are infinite number of bilinear distribution. The values of the random variable is 0, 1, but the probability may be different for different value of p. So there are infinite number of them, and each of them is indicate or indices by p. So different p gives you different bilinear distribution. And this p is between 0 and 1, and he has infinite number of possible values for p. And p is referred as the parameter, the unknown constant which characterizes or indices the distribution. All right. So for the collection of the distribution with the same form, but with different parameters, we call it a family of distribution. So we can talk about a family of bilinear distribution. And each member in this family will have the same form of the probability function, p to power x times 1 minus p to power 1 minus x. All right? But with different value of p, will give you different values, a different distribution. So sometimes 1 minus p is referred as q. So this is a nice way to write down the form. You can have another way to write it. All right, it is equal to P if x equal to 1, and 1 minus P if x equal to 0, and 0 otherwise. All right, or you can write it in a table form. X takes the value 0 and 1, and f of x takes the value 1 minus P and P. All right, so there are various ways to represent or to tell you what this probability density or probability function is. But usually it's better to write it as a mathematical form so that we can do further mathematics easily. All right. So for example, if I have two random variables, both are bilinear distribution. All right. Then what is the joint distribution of x1 and x2? All right. So my question is, if x1 is a bilinear distribution with parameter p, x2 is also a bilinear distribution with parameter p. So what is the joint distribution of x1, x2 if they are independent? All right. So if you write it in a table form, then how can I get the joint distribution? And if you write it like that, so how to find the joint distribution? But if I write it in a mathematical form, then the joint distribution with just multiply p x1, 1 minus p, 1 minus x1, times p x2, 1 minus p, 1 minus x2. All right, so it just, and it holds for x1 equal 0, 1, and x2 equals 0, 1. All right? Okay, so sometimes we can just write down the probabilities. All right, so I just mentioned this f of x depends on the quantity in this particular distribution or this example, bilinear distribution, the quantity is p. All right, and then numerous possible values for this p. P is between 0 and 1, which is infinite number of them. All right, so different values of p give you different bilinear distribution. All right, and this quantity is called parameter. So later on, when we talk about more of various family of distributions, then you have to aware of what are the parameters. So for bilinear distribution, there's only one, is the p. But later on, when we talk about binomial distribution, there are two parameters. All right, each have their own meaning. So here the parameter p represents the probability of getting a 1. If x equal to 1 is the success, then it means the probability of getting a success. So the collection of all the probability distribution is called the family of probability distribution. All right. Okay, so a bilinear distribution has a mean equal to p and a variance equal to p times 1 minus p. Now this again is the simplest distribution. Hence, to find the expectation of x and the variance of x are quite straightforward. All right. So recall what is the expectation of x, which is summation of x times the probability function. So in our case, x only takes two values, either 0 or 1. So it's 0 times f of x evaluate at 0 plus 1 times f of x evaluate at 1. So it's 0 times 1 minus p plus 1 times p. So of course the answer is p. So the expectation of a bilinear random variable is equal to p. Equal to p. P is the probability of getting x equal to 1. Right? So find the variance of x. All right? So you see, I always do the easy one. The harder one, you have to do it yourself, right? So expectation of x2 first. So according to the definition, is summation x equals 0 to 1, x squared f of x. So it is 0 squared times 1 minus p plus 1 squared times p. So again, it is p. Expectation of x equal to p, expectation of x squared equal to p. Let me sidetrack a bit. How about expectation of x cubed? X to the power 3. Huh? What is it? P again. Expectation of x to the power n is always p. Right? Because there are only two parts. One is 0 times the 0 raised to the power n. Again, it's 0 times the probability of x equal to 0. Then the other one is 1 to the power n. It's again equal to 1. So basically it's p. This is very, very special. All right, so we continue. Does it mean that the variance of x equal to 0? No. Variance of x is expectation of x squared minus the square of expectation. So it's p minus p squared. So p times 1 minus p. So that's the variance of x. Variance of x. All right? Now, so this is how you get a formula. So my next question to ask you is that, now I have this formula for the expectation of x and the variance of x. All right? So suppose I want to know what is the value of p such that the variance is the smallest. Right? So, how to get it? My question is, what is the p value, the value of p, to make the variance of x the smallest? 1. 1. When p equal to 1, is it a random variable? No, right? Yeah, you can choose the p as small or as big as possible, but it cannot be 0, cannot be 1. All right? So in fact, it is as close to 0 as close to 1. Then the variance is smaller. What it means is that if your p is very close to 0, let's say your p is 0.001, then what does it mean? It means that most likely you don't have any chance to get a 1, a very small chance to get 1. Most likely you've got 0. So the variation is very small, almost like 0. All right. So, okay, so this one is not clear. Only know that as p close to 0 or close to 1, then the variance is a bit smaller. Then on the other hand, so since I can ask minimum, then I can also ask maximum. So what is the p value? This one will give you the maximum value. Or does the maximum exist for variance of x? What is the x value that make this one the biggest? One way is to try to differentiate it with respect to p, right? So when you differentiate p times 1 minus p, what do you get with respect to p? You see, my point is that you don't just look at the formula. Okay, how to derive formula I showed you. So basically just follow the definition of expectation and the variance. The next thing is that how do you understand these two quantities? Expectation of x, in this example, and variance of x. So I would like to know what is the p value to make variance of x the largest. So definitely I will differentiate with respect to p times 1 minus p. That will give me 1 minus 2p. All right? So naturally, I will equate this equal to 0, and I got p equal to 0.5. When p equal to 0.5, does it give us the maximum or the minimum? You have to check another thing, the second derivative. So when you differentiate this with respect to p, you got minus 2. So you have to evaluate the second derivative at the point p equal to 0.5. But since the second derivative is equal to minus 2, it does not matter. All right, but you're supposed to evaluate it at p equal to 0.5. So 1 minus 2p equal to 0 implies p equal to 0.5 or half. So this one I evaluate at p equal to 0.5. And this one, it does not depend on p, so it's always minus 2. It's a negative. So in other words, at p equal to 0.5, okay, the second derivative is negative. So is the variance maximum or minimum when p equal to 0.5? Oh, all returns to your calculus teacher. So when it's negative, it's maximum. All right, yeah. Change the slope. All right, the slope of the first derivative is negative. Anyway, so p equal to 0.5. So in other words, the variance of x for Bernoulli distribution, it will be, the variation is the maximum when p equal to 0.5. So what does it mean? It means that if you are far away from p, or your p value is far away from 0.5, then the variation of your x is smaller. So I give you an extreme example. If p equal to very small, like 0.001, then most likely you won't get 1. It's most likely you got 0. So a lot of times that you got 0, but a few 1. So the variation is very small. But if it's p is 0.5, then you will sometimes got 0, sometimes got 1. So the variation is quite big. All right? So that's the idea. All right? So I want to use this simple example to illustrate how questions that you can ask and how all these expressions mean. Okay, look at this example. So I have a box, have 4 blue ball and 6 red balls. So if I draw a ball, 1 ball only, all right, 1 ball only from the box, what's the probability that we have a blue ball? All right. Now this one, without the distribution, you can work it out easily. All right, the answer is 4 over 6, or 4 over 10. 4 over 10. But I tried to look at this problem as an application of this Bernoulli distribution. So x, all right, equal to 1 or success if the ball taken out is a blue ball. And then 0 if it is not a blue ball. All right, so then x equal to 1 is 4/10 and x equal to 0 is 0.6. So I can write the probability function as 0.4 times x and 0.6 times 1 minus x for x equals 0 or 1. All right? And 0 otherwise. So in other words, probability of getting x equal to 1 is 0.4. All right? So you just substitute x equal 1 and you got 0.4. All right, here's another example. This example is prepare you for the Bernoulli distribution. So now we are considering taking the ball out. Okay, after we record down what outcome, what color it is, and put it back and take a second time. So we take a sequence, quite a number of this Bernoulli experiment, and several times, right? And they're independent, so that the p remains the same. Now, this is very important. If you take out a ball and you don't put it back, so the next time the probability of success, getting a blue ball in this example, will be different. For example, the first one you're taking out is a blue ball, so the number of balls, blue balls in the box reduced, as well as the number of balls in the box. So the p will change. It depends on whether it's the outcome, the first outcome is blue or not blue. So it's very complicated. But if you put it back, then you return to the to the original form. So you will have the same probability of success. So here, we assume that it is with replacement. Taking the ball, we've taken 5 balls. All right. Remember, here means that we are not taking the 5 balls at one shot. If you take 5 balls at one shot, then that means that you are sampling or you are taking out without replacement. All right. So it's just like you take 5 balls at a grab. It's just like take 1 ball, put it aside, and then try to take a second ball, and take a third ball, 4th ball, and 5th ball, and so on. So what we mean here is that you take 1 ball out, record down the color, and put it back. So that's called with replacement. So we put it back. All right. So let the draw of blue ball considered as a success. So, so we have a sequence of 5 Balloonia trials with probability of success is 4 over 10 or 0.4. All right, so I have the first one, the outcome. The first outcome is a Balloonia distribution. The second outcome is also a Balloonia distribution. All right, so now we consider n Balloonia trials. So let x1 represent the outcome, either 0 or 1. x2 represent the outcome of the second trial, and so on. And we have altogether n trials. That means you take n balls one by one with replacement. So the results can be represented by a sequence x1, x2 up to xn. And what are the value of x1, x2, xn? They are either 0 or 1. So a particular outcome will be like 0, 1, 1, 1, 0, 0, like that. All right. A particular example is 0, 1, 1, 1, 0, and so on. So this is a particular realization of the sequence of random variables. All right. So now I would like to ask, so if I want to know out of these five balls, how many of them, what's the chance that I will have, let's say, 3 blue balls? All right. So in other words, I'm doing 5 trials, drawing 5 balls or drawing balls 5 times. All right. What's the chance that I got 3 blue balls or getting 3 successes? So I would like to address this question. All right. I have 5 balls taken one by one with replacement from the box. What is the chance that I will have 3 blue balls? So to be more general, it means that if I have n Balloonia trials, all right, and each trial are independent and with equal chance of success, or the p is the same, then what is the probability that I got 5 successes out of these 3 successes out of these 5 trials? That's what I want to find out. So x, this is the beauty about the whole thing, the 0, 1 thing. So x can be expressed as a formula, the sum of all the x1 up to xn, the outcomes. So you can see that x1, x up to xn, they take value 0 and 1. So the sum of x1 up to xn will have a value which is the same as the number of ones. This sum tells you the number of ones, all right, out of this n random variables. How many ones are there? And remember what is 1? 1 represents success. So basically it's the number of success out of this n Balloonia trials. So x is what we would like to investigate. X is the sum of x1 up to xn. All right? So now the question is, what is this? Or what is probability of x equal to little x? The random variable x here equal to a particular value x. Now obviously, this little x can only be 0, 1. Can it be 2? You have n trials. Of course, you can have 2 successes, 3 successes, up to n successes, but cannot go beyond that. You have n trials. How can you have the number of success bigger than n? So at most, you have all successes, which means that n successes. So remember, here we fixed the number of trials at n. So your probability function for the random variable x, which is the sum of successes, the number of successes in this n trials. So we want to find out what is this probability, where x is equal to 0, 1, 2, 3, 4, up to n. So how to do it? All right, so we consider a particular sequence, very particular. The first x are successes and the remaining are failure. This is one particular outcome of all these n trials. X of them successes and n minus x of them are failures. So what is the chance to get this particular sequence? The chance of getting a success is p. The chance of getting this one is also P because they are independent. The outcome will not affect. For one trial will not affect the others. So, and this one is 1 minus P. So I have to multiply all this together so that at the end I got this. This is the probability that I got this particular sequence in that order. First X are successes and the remaining n minus X are failures. Alright? So this is the probability. But this one will give me X equal to X. Alright? For this particular sequence. But how about if I got this sequence? So there are one F here, and then here is m minus X minus 1 of them. Alright? And this one altogether, there are X of them. So this sequence also have probability P to power X times 1 minus P to power n minus X. Alright? This also give me X success. Alright? X success. So now the question is, how many such sequence? Okay, how many such sequence in arranging this n? All right. So basically, it is it just have to choose x numbers out of n. So there are so many sequence. Is it? All right. Choose x out of n. Choose x out of n. All right. So there's so many sequence which have the same probability. I just add all this probability together. It looks as if I multiply this number of sequence times this probability. That will give me probability of x equal to little x. All right. So you can think of it like this. Why this is n, choose x from n. All right. You can think of it. You have you name the box, the balls in the box. All right. Name them. Okay. So you name them 1 up to n. So what you have to do is to select x balls. It doesn't matter which one comes first. You just pick the x balls out of this n ball. That means take x numbers out of these balls. How many ways that you can take it? So it is n, choose x out of n, or cnx. All right, it's the same thing. All right, so it choose, the order is not important. All right, let me go back to the 5 balls. Okay, I have 5 balls. So I take 3 balls, for example. So I can take 2, 3, and 5. It doesn't matter whether it's 5, 2, or 3. The order is not important. So long as I have these 3 balls, you consider as 1. So basically it's a combination. I select 3 balls out of these 5 balls. So it just select n balls. Sorry, select x balls out of the n balls, or select x successes out of these n trials. So it's a combination. Okay? This doesn't matter. It just counts as a set have 2, 3 balls, 2, 3, and 5. All right. So this is the probability function for a binomial distribution where x equals 0, 1, 2 up to n, and 0 otherwise. All right. So this is what we call binomial distributions, and the 2 parameters are n and p. So different n, different p will give you different binomial distribution. A special case is when n equals 1. That means I only consider 1 trials. That will become a Balloonian distribution. So the PDF is given by this form when x equal to 0, 1, 2 up to n. Now, you have to understand this expression. It means the probability of x equal to little x. So in this case, n, p, and this basically is 1 minus p. So that 2 is a function of n and p and x. All right, while n and p are fixed. N and p are fixed. They are called parameters. X is the value, the possible value of the random variable x. All right? And n must be positive integers, and p lies between 1 and 2, 0 and 1. N range positive integers, so it's start from 1 up to infinity. All right? So, now this is important. What is x? If x is considered as the number of successes out of n independent bilinear trials, or sometimes we refer as dichotomous trials. That means there are only two possible outcomes. So you have two possible outcomes for each trial. Then you can name one as success, one as failure, or name one as x equal to 1 and the other as x equal to 0. So you must have n trials. And these n trials must be independent, which means that the probability of success are the same. All right? And also the outcome will not affect the other trials. And while x is the number of successes out of these n independent bilinear trials, then x will follow a binomial distribution. All right? So here are some three graphs to show the probability function for different p. So both n equal to 10, but this one p equal to 0.2. So in other words, the probability of success is smaller, only 0.2 chance of success. So it's likely that you will see the values, the number of success out of these 10 trials is around 1, 2, and 3. While if p equal to 0.5, you can see that it's likely to be 4, 5, or 6 is the number of success. The number of success most likely is 4, 5, and 6. While for p equal to 0.8, then it is about 7, 8, 9, 10. So you can see that when p is small, what do we call this? It's right skewed, because it's a long tail on the right side. So this one is right skewed distribution. This one is sort of symmetric. All right, symmetrical. This one is left skewed. Left skewed. That means they have a long tail on the left side. All right, the mean and the variance. For mean is n times p, while for variance is n times p times q. All right, n times p times q. So in other words, if x follow a binomial distribution with parameters n and p, you expect the number of successes equal to n times p. So if p is large, close to 1, then the number of success we expect the number of successes will be large, because it's n times p. If p is large, then of course np is large. Similarly, if p is small, then np is small. All right. So also the variance. So again, what is the maximum? When is it maximum? So you can check. So for fixed n, p equal to 0.5 will give you the maximum variation. Okay, for the proof, so some of you already worry about, would that be test? All right. Okay, the mathematics is a little bit, okay, there are at least two ways to do it. Recall, expectation of x is sum of x times f of x. Similarly, for the variance, you have to work out expectation of x squared, which is summation x squared f of x. But of course, through these methods, you need a lot of hard work. All right? There's an alternative way to do it. Remember, x equal to x1 plus x up to xn. What is the expectation of x1? x1 is the outcome for the first trial, which only takes 0 and 1. So the expectation of this one is p. It's a Balloonia. This one is a Balloonia distribution. All right? And what is variance of x1? I just showed you that it is p times 1 minus p. Okay, so now, what is the expectation of x? If you recall the properties of expectation, this is equal to expectation of x1 plus expectation of x2 plus up to expectation of xn. What is expectation of x1? P. What is expectation of x2? P. What is expectation of xn? P. How many p there? N of them. So it's n times p. Wow. So straightforward. All right. So I want to illustrate, you can follow from the definition of expectation of x. So it's summation x times f of x. While your f of x is choose x out of n and then times p to power x 1 minus p to power n minus x. So that will need a bit more hard work, all right, to work on it. Of course, if you treat it as a sum of set of random variables, x1 plus x2 up to xn, so the expectation of x is equal to expectation of x1 plus expectation of x2 and so on. While expectation of 1 is much easier to work with, we have already done it, it is equal to p. So it's p plus p plus p, so the answer is np. How about this one? If I want to follow the idea, if you recall the properties of variance is variance of x1 plus variance of x2 plus up to variance of xn. Is that it? Do I have other terms? x1, x2. Wow. I'm already had it. Haven't finished. The last one should be covariance of n minus 1 and xn. That means all possible pairs, all right, of xi and xj with I less than j. 2 times it. Or, okay, all possible pairs. So x1, x2, covariance of x1, x2, covariance of x2, x1, and so on. Many of them. But what is covariance of x1, x2? 0. We want it to be 0. But why is it 0? It's not because you think it is 0. It is 0. Why? Yeah, sometimes you wish, this one is 0. Right? No, because they're independent. All right, xi and xj. That means any of the, in this sequence, that means the outcome of the ith trial is independent of the outcome of the jth trial. So therefore the covariance is 0. So I don't bother. You see the difference is that I know that all these are 0. All right? You may have a wishful thinking, the variance of x equal to variance of x1 plus variance of x2 up to variance of xn. So this time you're right, but may not be so lucky next time. The problem may not have the properties of independence. Then you have to work out the covariance. This time, yes, they are independent. So, what is variance of x1? P times q. All are p times q. How many of them? N of them. So that's why npq. So it's not just by coincidence. It can be shown that it's equal to pq plus pq plus pq and n of them. So it's npq. And one more thing, just in case you want to do some algebra on this part. So you remember one of the properties about this. Remember? What is the sum of all the probability function? Equal to what? 1. So in other words, you can make use of these properties, x from 0 to n, x choose out of n, p to power x, 1 minus p n minus x, this is equal to 1. All right? This is equal to 1. So this one is very useful. Sum of all the probability function, so sum of all the sum over x for all the probability function is equal to 1. This is property. So what is this? What is this? 1 minus x. So this is also 1. Why? Because this is a probability function of a polynomial distribution. So it's also equal to 1. All right? Okay. So much for the mathematics. So these are the conditions that you have to remember to check. Or at least you understand that your problem has all this. Okay? You have n repeat polynomial trials. Repeat means that the conditions are the same. So probability of P, probability of success is P, and they are independent. All right, only 2 outcomes for each trial. If it's more than 2 outcomes, then the problems is more complicated. We use different distributions, which we are not going to discuss. All right, so the probability of success is P, and same for each trial, for all the trials. And finally, the trials must be independent. If it's not independent, then we have problems. We cannot model by binomial experiments or binomial distribution. So x is the number of success out of n trials. All right, so that x follow a binomial distribution with parameters n and p. Just remember, x is not just the number of successes. X is not just the number of successes, it's the number of successes in n independent polynomial trials. Independent trials. Or at least you have to know that it is from n trials. X is the number of success out of n trials. All right? Okay, so let's look at some examples. What's the probability of serving exactly 6 heads for unbiased coin flipped 10 independent times? So obviously, we have 10 trials. All right? So this is n. And what we want is to ask what is probability of x equal to 6, where x is the number of success or number of heads out of 10 tosses or 10 flips. So this is 10 trials, and x is the number of success out of n trials, out of 10 trials. So we are asked what is the probability of x equal to 6. All right? So usually when you try to solve this type of problems, you must first define what is your x. So in this case, x is the number of successes, out of n trials, independent trials. For a toss, you have only a head or tail, or success or failure. In this case, getting a head is considered as a success. So x, because it's an unbiased or a fair coin, so the probability of success will be 0.5. So we have x follow a binomial distribution. So in other words, once you define what your random variable x is, in this case it's the number of success out of 10 trials, or number of heads out of 10 tosses, and then you try to write down the distribution of this random variable x. So it follow a binomial distribution with n equal to 10 and p equal to 0.5. All right? So we just work out x equal to 6. So apply the probability, the definition, so we got it 0.205. So the chance getting 6 heads is about 20%. All right? So there is, okay, sometimes we can use a table for statistical tables for binomial. So for the table, we will have 2 numbers fixed, n equal to 10 and p equal to 0.5. Then look at the cumulative probability, x greater or equal to 6 and x greater or equal to 7. Then this difference will give you probability of x equal to 6. All right? So that's one way to do it. So this is the table that I mentioned. So this one for n equal to 10, all right, n equal to 10. And if p equal to, in this case, is 0.5, so this number, 0.38, okay, maybe I make it bigger, more decimal place. Oh. Okay, so you can see that probability of x greater or equal to 6, the probability is 0.377. And the probability of greater or equal to 7 is 0.719. So the difference of these two will give you the answer, probability of x equal to 6. All right. So you can see that this table, you need to specify the p, which is 0.5 in our case, and you have to get your x values. So that will give you the tail, upper tail probability, means that probability of x greater or equal to the little x. So this means that the probability of x greater or equal to 6. And this number is the probability of x greater or equal to 7. So the difference represents probability of x equal to 6. And what is the command? In Excel, you can use this binomial dot dst, and there are 3 or 4 arguments. The first one is your x. The second one is your n. The third one is your p. And the fourth one is a true or false for whether it is cumulative or not. So for example, if I put 6, 10, 0.5, and true here, or false here, then this statement will give me this as the answer. Because I don't want the cumulative, I only want exactly equal to 6. If you want the cumulative, then it will be true for the last argument. But this will give you probability of x less or equal to x. All right, if it's 6, then it's less or equal to 6. So you won't get this number. If you want to get this number, it will be 1 minus 5. To get this number, the statement that I use is 1 minus binomial dot dist. These are for Excel, for Excel. So 5 and p and true. Okay, so I subtract it from probability of x less or equal to 5. So the remaining is x greater or equal to 6. It's just for you to calculate in case you have the computer, you have access to Excel or some other software or your graphic calculator. But on the other hand, you also have to know if you are given a table like this just now, like the table that we have, you have to know how to read the table. All right, let's look at example 2. So suppose a child recovers from certain disease with probability 0.2, and suppose there are 20 children are known to contract the disease. So what is the probability of at least x survive, or between 2 and 5 survived? Here we make an assumption whether a child recovers or not is independent of whether other child recovers or not. Otherwise, you cannot model it by a binomial distribution. So in this case, x, all right, will be the number of kids that recover, who recovers from out of 20 kids, all right, who contract the disease. So x follow a binomial distribution with n equal 20, and p, the probability of recover is 0.2. So the first question that we translated into a probability statement is at least X survive. That means X at least equal to X. So it has to be bigger or equal to X. So what is the probability? X. The number of kids recovers is at least X. That means it can be 8, can be 9, can be 10, up to 20. The second statement is to get the probability of X between 2 and 5. What is the chance? So we are supposed to answer to find these two probabilities. So you must define what is X. It is the number of successes out of n trials. Identify what is n, identify what is p. And then translate your questions into a probability statement involve X. All right, so in this case, at least X means X greater or equal to X. So now, this one I can read out from the table that I give. All right, so or this one you have to pay attention. It is probability of X less or equal to 5 minus probability of X less or equal to 1. All right, or basically it's like this: X less or equal to 5 minus probability of X less than 2. X less than 2 is the same as X less or equal to 1. Because it's a discrete random variable. Take the value 1, 2, 0, 1, 2, 3. So less than 2 means that it is less or equal to 1. All right, so this is 1 minus probability X greater or equal to 6. This is 1 minus probability X greater or equal to 2. So I read out from the table these two values, and this is the answer. So this is the table. This time n equal to 20. N equal to 20. Again, it's still upper tails with p. P is 0.2 up to 0.5. Then probability of X equal to 2 and 5. Okay, so it is this one minus this will give you probability between 2 and 5. And what's the other one? At least 8. So it is 1 minus this number. 1 minus this. All right? Oh, I'm okay, sorry. These are the upper tail. That means, so X greater or equal to X, so you can read out directly from the table. All right? Just now I think of the Excel. All right? It's funny, 0.1, 0.15, 0.2. So what happens if P equal to 0.18? In the exam, if you are not allowed to use any calculator, no computer. So if P equal to 0.8, then what to do? What is the probability of X greater or equal to 2, for example, when P equal to 0.18? So what to do? I don't know. Give some idea, give an approximation. So P equal to 0.18, right? I asked, when P equal to 0.18, what is the probability of X greater or equal to 2? So I will choose, all right, it's somewhere between these two numbers, am I right? Right? So you have two options, at least. Take the average of these two, because it's between P equal to 0.15 and P equal to 0.2, right? So 0.18 is between these two. It's not exactly in the middle, but you take the average of the two. That's one way. Alternatively, what is the alternative way? I don't take the middle ground. I favor one, so I pick one. So which one you take? Take the nearest one. Take the P equal to 0.2, right? Take the answer. P equal to 0.2. All right? Now, let me ask another question. Okay, P equal to 0.2, but I ask what is the probability of X greater or equal to 2.5? This one, you cannot take approximation. You must know probability of X greater or equal to 2.5 means that it is equal to probability of X greater or equal to 3 or X greater or equal to 2. Let me write it down. Yeah, don't know why people put a table there. All right, look at this table. now my question is, if I give P equal to, just now I asked when P equal to 0.18 from the table, how to get this answer. So I suggest two. One is to consider P equal to 0.2 and P equal to 0.15. Take the, under these two P's, take the probability of x greater or equal to 2 and take the average. Or you just take the one closest. So to me, seems that this one should be close to 0.18. So that's one way. So now I have another question. So when P equal to 0.2, what is the probability of x greater or equal to 2.5? Oh, just now you mentioned take the average. So now I take the average of probability of x greater or equal to 3 and probability of x greater or equal to 2. Take the average, which is wrong. All right, I just want you to know that. So this one should equal to what? Can it be probability of x greater or equal to 2? No, right? So it has to be greater or equal to 3. All right? Okay? Am I right? I may be wrong, huh? Okay. And one more thing that in fact I want to mention. So for this table, up to 0.5, how about if P equal to 0.6? Sorry, you don't give me the value, how can I use it? How? Hey, success and failure can swap their role. So, if P equal to 0.6 is the probability of success, then I change it. Your success become my failure. So, the probability of success will, I just reverse my definition of success and failure. So, if in your case, success have a probability 0.6, so I reverse it, I call it failure. So now your failure has a probability 0.6, so success will be 0.4, so I can use the table. All right. Of course, you have to change your probability statement. So if your x is success and x greater or equal to 2, now you have to reverse it, change to x less or equal to 2. Why? Okay, that's so all this little thing it's not just to use this table, but let you think about it, understand that your success and failure, the role, how you define success and failure can be swapped. But you have to change the whole setting accordingly. So you translate your probability statement accordingly. All right, it's too much for that. Okay, let's go back. All right, so here's another example. I think this example is more or less the same idea. The idea is like this. So someone claims he has the sensory perception. That means they have people don't have the abilities. All right, so they can guess, correct? So suppose he gets 7 out of 10 correct. So does it support that he has this kind of abilities? All right. So it's very easy to find, to check. So you ask yourself, how likely for a normal person that you can identify 7 or more successes? All right? Identify 7 or more correctly. All right? So, why 7 or more? 7 or more? Because just getting 7 is not good enough, right? You have to consider the chance of more extreme than what you see, 7. So including those 8, 9, and 10. So how likely you will get correctly identify 7, 8, 9, or 10 correctly out of 10 trials? So, this is the key. If you and me guess, so guess correctly and incorrectly is 0.5. All right? Because there are only 2 outcomes, either for success or failure. We assume that is equally likely. But it's different for multiple choice questions. If there are 4 choices, you guess. The chance of guess correctly is 1/4. If there are 5 choices, the chance of correctly identifying it by guessing is 0.2. But usually MCQ will not have 10 options for you to choose. Otherwise, make sure that you study. Otherwise, you guess, it's most likely you guess wrongly. All right? Okay, so these are only 2 choices, so it's chance of success is 0.2. So the number of answer correctly followed by normal distribution, 10 or 0.5. So we are trying to calculate the probability of a normal person. How likely it got 7 or more questions correct or guess correct. So this one is just to illustrate. In fact, you can read out from the table, the answer is 0.1719. Is this a small number? I don't know, maybe to you it's small, but to me it's not. As for statisticians, they already used a number for many decades. The number is 5%, or 1% sometimes, all right? So less than 5% is considered small, all right? So in this case, it's not that small. What does it mean? It means that for a normal person who does not have this extrasensory perceptions, he can get 7 or more correct. The chance is 0.17. You may wonder, why don't you just calculate this? You see 7 now, so calculate this probability. Is it okay? No. If you just look at 7, then those who got 8, 9, or 10 also indicate that it's still normal, but you got 8, 9, 10. There's some chance like that. You cannot just look at 7 itself. You have to look at what is the chance that you got more extreme than what you see. All right? So then you will find out whether this is reasonable. If the chance is very small, if this number is very small, if it's 0.01719, for example, then we say that, okay, now the chance of a normal person get 7 or more correct is only 0.017, very small chance. So if you're able to achieve 7 correct, then I think that you really have some ability, which is ordinary people does not have. All right? But in this case, it's not. Let's think of it. To put it more extreme, I toss a coin. I tossed it 10 times. I got 7 heads. Do you think it's likely or unlikely? So this tells you that it's not that unlikely. The chance that you got 7 heads out of 10 tosses is about 7 or more. 7 or more is about 17%. Not that small. But if I put it more extreme, if you have 100 tosses and you get 70 heads, so do you think that the coin is fair? All right? So I ask you this question. If X is the number of success, number of heads out of 100 toss with a fair coin, what is the probability of X greater or equal to 70? Work out this probability, if you can. All right? Then you see this probability, in fact, is very small. All right? Okay, I guess it's smaller. Okay, you check it out. So in that case, that's not that common to have 70 heads out of 100. All right? Okay, so I think I skipped this example 4. Example 5. All right? Now, for example 5, this manufacturer claims at most 10% of its product, all right, needs service under the during the warranty period. So these technicians take out 20 units and test each under this accelerated testing, all right, to find out whether it fails or not. All right. Now, the problem is like this. The manufacturer has some claim about the probability of sending for service during the warranty period. This item is a power supply unit. Don't worry about what what product we are talking about. Just 10% of chance that it need to surface during the warranty period. That's what he claims. But maybe he is wrong. Maybe his product is so good that it's not 10%, maybe only 1% that need to be surfaced during the warranty period. Usually it's not the case. Usually manufacturer will try to under-declare. So now we are worried about whether P is in fact more than 10%. That means more than 10% require needs surface during the warranty period. So this technician tried to show some evidence. So take out 20 units and try. Okay. So now here we assume that P is 10. P. Just let it to be P. So the whole problem is like this. All right. I look at 20 units. I try each, see whether they need service or not within the warranty period. All right. And so we decide on the data whether we accept the claim that the P is 0.1. P is the probability of sending for service. So X is the number of units among these 20 that need repair, and X follow a binomial distribution with n equal 20 and P equal to P. Probability of success is P. I did not specify what is P at this moment. It just formulate the problem. So the manufacturer claim P is less or equal to 10%. All right, just take 10% for example. All right, but we suspect maybe P is not 0.1. So why is it binomial? So you should know that because we have 20 trials, 20 units. Each unit is considered as trial, and each unit is either need or does not need the repair. All right. So now, the technician's decision rule is that, okay, I will reject this claim if I find out that there are more than 5 units need repair. So that's his decision rule. All right. So out of these 20, if the number of units is more than 5 that need to send for repair, then the P is not 0.1. All right. While if the number of units that send for repair is less or equal to 4, then we will accept this statement P equal to 0.1 or less or equal to 0.1. So the idea is very simple. If P is big, I expect more units out of this 20. So how big is big? So I set a line. Okay, if X is greater or equal to 5, I would say that P is very big, bigger than your 0.1. All right. But on the other hand, if the number of items need for repair is very small, like 0, like 1, 2, 3, or 4, I will believe that P is less than 0.1. All right? So, no matter what you do, no matter what decision you make, there's always a chance that you may make the wrong decision. All right? So we accept that. But we want to minimize the chance of making a more wrong decisions. All right, so we'll do the following. So suppose, all right, P is 0.1, and we reject it wrongly. So in other words, we are looking at, suppose the P is really very small, for example, 0.1. But if the number of items need repair out of this 20 is bigger or equal to 5, we make a decision. You are wrong. P is bigger than 0.1. All right? So this one is suppose P equal to 0.1. Then we make the decision. We reject the statement P is less or equal to 0.1. So this is wrong. All right? Or we reject it and claim that we reject this statement and claim that P is bigger than 0.1. P is bigger than 0.1. So this is wrong. So we will try to work out how likely I make a mistake. And it turns out that, so this one you have to work out. So in other words, try to get the probability of X greater or equal to 5, given that X follow binomial with 20 and P equal to 0.1. Work out this. All right, 0.043 is considered as small. So that means my decision rule will make sure that I will reject wrongly the manufacturer's claim with a very low probability, only about 4% chance. Seems okay. But what happens if the probability of send for repair is not 0.1, but in fact it's 0.2? All right? So, what's the chance that I make a mistake? When P is 0.2, I still believe P is 0.1. I still believe P is 0.1. So that means I make a mistake. All right? You have to understand this is the underlying, the fact that assume. While x less or equal to 4, when you have x less or equal to 4, when you take 20 and you find that the number of items need repair is less or equal to 4, then you decide, okay, I believe P is very small. It's less or equal to 0.1. But in fact, it is 0.2. So I make a mistake. I commit an error. So here we are looking at where x is binomial, 20, and now I change P equal to 0.2. And so I work out this probability, it turns out to be 0.6296. So this number is quite big. So in other words, you commit the error with very high chance. So this decision rule, you cannot say that, okay, when x is less or equal to 5, the other, okay, you can only, you cannot change. These two are complement of each other. You cannot say that, okay, x greater or equal to 5, then and then also the other one is change this to 6. No, you cannot do that. It must be complement of each other. All right, so you can only change this number. So maybe you change it to 6, change this to 5. It's okay. Then you have to reward the probability. Okay, my original, all right, so I set my cutoff as 5. Greater or equal to 5, make a decision. Less or equal to 4, I make another, my decision will be I accept or I do not reject the manufacturer's claim. But if I see more need to repair, I don't believe in manufacturer's claim. So that's the decision I make. All right? But the probability of committing an error is great. So I will tell the technician, don't use this decision rule because this will in a disadvantage for me. If P is 0.2, now the chance that you will see some x less or equal to 4 is still quite big. All right? And then by this outcome, you will not challenge the manufacturer's claim, which is less or equal to 0.1. All right? So I just want to use this for the two purposes, this example for two purposes. One is to illustrate how to calculate these probabilities. So here I change my P. Different P equal to 0.1 and P equal to 0.2. All right. So I try to work out the probability. So, but the first one has an interpretation. That means when this is true, what is the chance that you will reject the claim that P equal to 0.1? This is another probability, which is when P takes different values. And what's the chance that you will accept P equal to 0.1? So you can think of it. This one, we assume that this is correct. Then if you see this one, you will make a decision of rejecting this statement. And how likely this mistake? Only 4%. On the other hand, if the true P value is 0.2, then you do not reject. That means you still believe P equal to 0.1. The chance is 63%. So it's very likely that you will, something is big, the P is big, but you still believe that P is small. So that is not good. All right. And this idea will be mentioned again when we discuss about hypothesis testing. All right. So, okay, negative binomial. Yeah, negative. This one is similar to binomial, but again, it's different. What it's, okay, in binomial, what we are interested in is x is the number of success. While in negative binomial, x is the number of trials. So what's the difference? This is the number of success in n trials. So the number of trials is fixed. This is the number of trials to get k successes. So we fix the number of successes and see how many trials that in order to get the success. Right? So they are different. One is the number of success with fixed number of trials. The other one is the fixed number of successes and see how many trials. So of course, this x must be greater or equal to k. This one, x must be less or equal to 1. All right? So in a binomial experiment, you just have each trial have 2 outcomes and you fix the number of successes and see when you have k successes. All right? So, for example, I need to have the 5th successes occur in the 7th trial. So in other words, the 7th must be a success, all right, with probability p, okay, success. And the previous one, I can have 5th success. So I can have 4 successes and then 2 failures. All right? Different arrangement, but I need 4 successes and 2 failures in order to get the 5th successes in the 7th trial. So the 7th trial must be a success. And before that, it has to be 4 successes. That means 5 minus 1 and 2 failures. So that will give me, all right, the 5th successes occur in the 7th trials. So it can be like this, can be like this. All right? So the probability of getting this sequence is P5Q2. This one also. So basically, you just count how many sequences. That will give you something like this, with the 7th being a success. So basically, you just have to permute how many successes? X minus 1 successes and, X minus 1 trials. And how many successes? K minus 1. So you just have to figure out how many sequences that you can have for X minus 1. All right, X minus 1 terms. And you have to have, among this, you have K minus 1 successes. So the probability or the number of choices here is choose 4 out of 6. These are 6 trials. And then you need 4 successes. So, the probability of getting 7 trials to get the 5th success, all right, we specify a 5th success. So it is choose 4 out of 6, and then P4, Q6 minus 4. This part is the probability of getting 4 successes out of 6 trials. The 7th must be a success, so it's P. And the number of choices, number of sequence is choose 4 out of 6. So this is the probability of getting X equal to 7 for the 5th, for 5 successes. Now these 5 successes the 5th one must be at the 7th trial. It's not any combination, but the 7th must be a success. So this is the general formula. Probability of X equal to little x is equal to Pk, K successes, and the rest are failure. But this part, all right, is X minus 1, K minus 1. And the last one is 1, 1. So it's like that. All right. So in other words, I divide the number of trials into 2 groups, X minus 1 and 1. So this one, I have to fit K minus 1 success. I have to put K minus 1 success. this one must be a success. So you choose 1 out of 1. Okay, so the top one is the number of trials, X of them. The second, this is the number of trials. I divide it into 2 groups, X minus 1 and 1 trials. And the second entry here is the number of success. I also divide the number of success into 2 groups. K minus 1 successes go to this K minus 1. The other one is the success must go to the last one. So this is 1, so it's equivalent to this. So this is the formula. And what is the X value? X equal to K, K plus 1, K plus 2 up to infinity. So that's the negative binomial distribution. And we can show that the expectation of X is K over P, and variance of 1 minus P, K over P square. So I don't go into the details of the proof. So we just have these properties. For those who really curious, if I want to apply the tricks of this one, up to n, all right, you can try. This one follow a geometric with probability p, a geometric distribution. If you recall, the geometric distribution that we mentioned in chapter 3, we talked about it briefly. So it's the number of trials before you get a success. So it's like this. So you got failure, failure, until you got the first success. So this is my x1. Then I try again until I got the next success. So this is the number of trials. That's the x2, the numbers. All right. So it basically just add up all this together. All right. But if you don't get this one, don't worry. I mean, you will not be asked. All right. But this one simple way to prove it by making use of the knowledge about geometric distribution. Anyway, okay, so here's an example. Okay, for NBA Champion Series, I think for a lot of American sports, the final champion series is like that. You have final 2 teams. It's not just 1 game to decide on who is the champion. They usually play 7 games. So who got the first 4 wins will get the title. All right. It's not just 1 game to decide. I think for a lot of our like soccer games, it's one game to decide who is the winner. But for a lot of American sports, so in this case, the National Basketball Association, I don't know, the NBA is, all right. So they decide the last 2 teams, all right, in the final, they will play 7 games. They play games until the one who got 4 wins, 4 games. So at most 7 games will be played. All right. You won't play 8 games, right? So, okay. So now suppose Team A has a chance of 55 winning a game. All right. So what is the probability that a Team A will win the series in 6 games? Now, so here the success is Team A wins a game. All right. It's considered a success. So we play. All right. Many times, all right? Each time Team A has a chance of winning is 0.55. So we ask, what's the chance that the Team A will win the game in 6 games? So in other words, we win, lose, win, lose, something like that. But we want the sixth one to be the winning game. And not only that, there are 3 W's in the first 5 games. In the first 5 games, there are 3 winning games. So the 6th one is winning for the Team A. So we would like to ask, what is the chance that it will win in the 6 games? So we consider the number of winning. I mean, the number of games that have to win is 4. It's not mentioned in the questions. Is it mentioned in the question? Yeah, winning the series. This example is for US. So they know that they have to win 4 games. So win 4 out of 7, the best 4 out of 7. So win 4 games out of win the 4th wins in the 6th game. So what is the probability that the Team A win the series? So, first of all, I define my X. X is the number of games that Team A plays, all right, in order to win 4 games. So in this case, X follow, in fact, I wrote down. So X follow a binomial with K equal to 4 and P equal to 0.55. All right, winning a particular game is 0.55 and K equal to 4, winning 4 games. So the first question is, what is the probability of X equal to 6? Okay, now the second question, what is the chance that he wins the series? So he may win it at 4 games. That means playing 4 games, Team A wins all the 4 games, so he wins the series. Or X equal to 5, or X equal to 6, or X equal to 7, or X equal to 8. Do we need this one? Oh. What I'm trying to tell you is that you don't have this, because the game will stop. The chance that he win 8 is not being considered, because that means the other team already win 4 games. So we'll get the champion. All right? So in other words, you can not blindly apply it. So only up to 7. Win 7, that means the Team A wins 4, while the other team wins 3. And this 4th win appears in the 7 games. So we just add these probabilities. So this is how we got the answers. All right, so these are, so winning at the 6th game is 0.18. Winning the whole series is 60%. So it's slightly higher chance than the other team. The other team will be 1 minus this number. The Team B will have 40% chance winning, while Team A has 60% chance winning. Now I have these questions. For one game, Team A has 55% chance of winning, right? While for the series, getting win the series, that means winning 4 games. So long as they play until one team get 4 wins. So the chance of Team A winning the championship or winning the series is 60%. It's better, right? What is the implication? It implies that if you are the inferior team, if I'm Team B, I don't want 4 out of 7 games. I want just 1 to decide on the winning. All right? Right? So if I'm getting more extreme, not 4 out of 7, but let's say, how many? 11 out of 20 games, or even worse, 51 out of 100 games, then it's closer and closer. Team A will getting higher chance to win the series. All right? So 1 game, 0.55 and 0.44. While 4 out of 7 is 0.6 against 0.4. So that will give you some idea. So how should play the games or define on the rules. So American way of doing things is fair. If you're a good team, the chance of winning the series is higher. All right. I think this also example 2. I think this is the geometric distribution. Okay. So P is the probability of BC. All right. And we need 5 attempts to get a successful call. All right. So probability of success is 0.05, and we only need 1 success. I just want to get through. So I only have 1 success. I'm interested in only 1 success. I don't bother about how many success. Just 1 success, get through. All right? The chance of each attempt to get through is only 5%. So what is the chance that I got through in the 5 attempts? So this is called geometric distribution. It's referred as the first success. While negative binomial refer to the K success. k successors. Here only the first successors. So here it is. It's a negative binomial with n equal to k equal to 1, or this referred to as geometric distribution. All right, so this is how we got the answer, 0.041. Now, here maybe you can try this one. So when x is a geometric series, it means that f of x equal to n equal to 1. All right. So you have x, choose 1. X minus 1, choose 1 minus 1. And then this one is what? P times raised to power 1, and then 1 minus p x minus 1. Okay, maybe let me write this. In fact, for geometric series, we only have one parameter p. The f of x is equal to 1 minus p to power x minus 1 times p. All right? For x equal to 1, 2, up to infinity. This is just to substitute k equal to 1 in the negative binomial. Now, based on that, you may be able to prove that expectation of x equal to 1 over p and variance of x 2 over, I have to check the previous, what is the negative binomial? Yeah, okay, so it is 1 minus p over p squared. You can show that. 1 minus p over p squared. Okay, if it's just for your interest, it's not, don't worry about the proof. I just let you know that it should be easier to prove this one because one important mathematics that involved. I don't know whether you remember the geometric series. This is equal to 1 minus r. Or a particular case is up to r to power k, let's say. Then this is equal to 1 minus r k plus 1 over 1 minus r. These are the property of geometric series. Geometric series. It will be useful if you know some of these properties about series. But don't worry about the proof. I just mention it for those. What you need to know is geometric distribution is concerning about the first success. While negative binomial is a number of trials to get to k successes. So geometric series is a special case of negative binomial. Geometric series is only the first occurrence. Like you call this to the always PC. So you want to know what is the chance that you'll get through. How many attempts that you need. So you just need to get through once. You don't bother about, how many times, what's the probability I got 3 times success to get through the connection. No, I just need the first one, all right, to get through. How many attempts that I need? So that will fall modeled by a geometric series, which is a special case of negative binomial. Okay, so I stop here. So tomorrow we'll continue with the Poisson and other distribution. And remind you about the test tomorrow evening at 8 o'clock.